This short tutorial wants to go through and shows you how to do the number of protons, neutrons, and electrons in any element, be able to draw the orbital diagrams, be able to pick out the valence electrons, and then show the electron positions in terms of electron configurations. We'll do it both as the long form and as the short form. From the periodic table, let's go ahead and pick Selenium. Selenium's way over here on the side of the periodic table in the oxygen family. So our first question is how many protons, how many neutrons, how many electrons? Well, the little number in the corner here, that is the atomic number. So we know that there are 34 protons. Then looking at the atomic mass down here at the bottom, we say it's really close. We could round that off to 79. So we know that selenium must be mostly formed from selenium that weighs 79. And we're going to say if we subtract those two, then we have 45. And that 45 is the number of neutrons. So this kind of an atom weighs 79 because it has 34 protons, 45 neutrons. Now we're also going to assume that this is neutral, and if it's neutral it must also have 34 electrons. So looking at the atoms, we can say it's 34 protons, 45 neutrons, 34 electrons. We'd like to be able to go back now and say, where do these electrons exist in the atom? We're going to put them into the orbital diagram, and starting down at the 1s, we have 34 electrons total. So here's 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now notice at this point we want to go over to the 3D because those are the next highest energy. So here we have 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, and 34. So this would be the orbital diagram for selenium, 34 electrons. Now at this point we can say, oh, okay, if you were going to bump into this atom, you would bump into these fourth floor electrons, the fourth level electrons. Not the 3s because they're still on the 3rd floor, so these would be buried down below, but you would bump into the 4s and the 4p electrons. We'd say we have 1, 2, 3, 4, 5, 6 valence electrons. Another way to show this is to use the electron configuration. Now I could go back now and say, okay, electron configuration, just start with the first orbital down here, and we have in that 1s orbital we have 2 electrons. So we would draw this sort of as 1s2. Then we can go back and see we're going to put 2 electrons in the 2s orbital, and so we'd say it's 1s2, 2s2. And if we continue like that, we'd see we'd have 6 electrons in the 2p. So we have 1s2, 2s2, 2p6. Continuing on, 3s2, 3p6, 4s2, 3d10, and 4p4. Now, we call this our long form electron configuration, and it is kind of long and unwieldy, so we go back and say, well, this many electrons back here, all filled up, kind of looks like the noble gas argon. So we're going to use the symbol argon in brackets and say these electrons belong to argon. Who do we have left? Oops. We're going to say argon, and we still have 4s2, 3d10, 4p4. And then if somebody said, well, which ones are the valence electrons? The ones level 4 are the ones that we would be bumping into first, so those are our valence electrons. That's it.